So today I will tell you how I got an upstream kernel running on a thermal camera. But before I start, let me introduce myself. So I'm a kernel engineer at Collabora and a maintainer of the power supply subsystem. I am a developer in Debian, and for today's talk, actually quite relevant, I co-founded a hackerspace in my city, and I'm active in the fire brigade as a diver. And at the fire brigade, from time to time, we're using thermal cameras. So let's have a look. What's a thermal camera? They're basically similar to a normal camera, but they're for sensing a different part of the spectrum. Like with a camera, you basically have a sensor that sees visible light. And for a thermal camera, it instead catches infrared. And usually the resolution is quite a bit lower than from what you used from your smartphone nowadays. Like on the kilopixel area, think about a really old digital camera from like years ago. That's about the resolution that you usually get from them. There's different reasons for that. One of them is the US actually has quite hard export restrictions on those sensors. So you're not allowed to, sell sensors with more than 9 frames per second or with a dense pixel size, because those kind of sensors are used for all kinds of things, and among others, one of it is target search. So if you have like a rocket and you want to have like automatic target following thing, then those kind of sensors are being used. Apart from that, as I just said, we're using them at the fire brigade to like do, for example, searching for persons if they are lost, and also if they are doing firefighting and they are wondering, okay, where's actually the fire? I can only see smoke. Then those cameras are being used to, find the source of the fire. Apart from that, because it's not using visible light, they perfectly fine also work at night. Does not really matter. There does not need to be any visible light. And as I said, I'm active in the hackerspace. So in electronics works, those kind of devices are used for fault searching. So why is this really interesting? Well, yes. Right. I'm not sure how that happened. Yeah, that's, okay, let's start again. So where were I? Well, I guess so far it was just the same that I just said. So, right, so how does it really matter? So the problem is those cameras used to be really expensive. There's effectively, one really well-known vendor of those sensors named FLIR, and their sensors are really expensive. And they're usually only used by manufacturers who are also known to be rather expensive. For example, the camera that we're using at the fire brigade is about 2,000 euros. So not that nice for a hobbyist. But then, like about a year ago, I found a quite cheap one from a Chinese vendor, which interestingly is 25 frames per second. So quite a bit more than what is restricted by the US. I didn't look into the details. I suppose one reason is, they're not based in the US, so they don't really care. And my plan was to just look into it and see what I can do with it, play around. And just a week later, somebody at my hackerspace was having a problem with the PCB and asked if he could use my camera, which, looked like this. So the spot that you're seeing is a bad soldering connection. So it was just like doing a single image, get up the soldering iron, fix it, and be done with it. A job of 5 minutes that otherwise would have taken quite a bit of time. The problem with that camera is the software is, not so nice. It needs between 30 seconds and a minute to boot up. And as you just have seen in the image that I included in my slides, there's all the overlays inside, including the battery icon. And obviously, if you take a picture after a year, so this image is a year old about, you don't really care that the camera was full at that time, so I would like to have those removed. Also, it's quite laggy. And another issue that I noticed is, so the scaling of the colors. If you look here, you have the dark parts that go into blue is cold, and then it goes to white for when it's getting hotter. That auto scales, and you cannot disable that feature, which means if you move the camera around, the colors are changing all the time, which sometimes is useful, sometimes it's really annoying. So my idea was, let's try to replace this. Which first of all meant I had to open it up and look inside. Let's see what I got. I found two different PCBs, one of them with the display and then another one with the sensors inside. So my next step was, okay, what did I get? So my way of procedure was, let's look at the chips, put the names that I find in Google and check what they are. So on this side of the board, I just found an eMMC chip, not that interesting to replace software at the moment, a bunch of debug pads that were nicely labeled. And I really mean nicely labeled, like they were labeled like OK, left, right, so I found out the buttons. Then 4 interesting pins, and my assumption was that might be a serial interface, but those were not labeled. So the easiest thing to do is, let's look on the other side. There were a bunch of more chips. I found memory, then a bus receiver for the display, and also a CPU, an IMX one, and I thought, great, that supported upstream quite well. So, looks good so far. And then the 4 pins from the other side. On this side, they are actually labeled with AX, TX, and ground. So, most likely they are serial. But before attaching a serial adapter, I was having a look at the other module. And interestingly enough, that also has 4 pads. And might be a little bit hard to read, but if you're looking from the back, you can actually also see labels on that one. And they are also labeled AX, TX, ground, and 3v3. So apparently it's also a serial interface. So next, I got out my soldering iron and added some pins to those pads. In this case, I figured out that there would be enough space inside of the case to just have the pins inside and not use pogo pins or whatever to get attached to it. And next, I was making sure that I'm actually using an adapter with the right voltage, because using the wrong one, you can quite easily break those pads. It almost happened to a colleague of mine, so always make sure to use the right voltages. But then afterwards, I was wondering, well, it would be nice if I can close the case and carry it around with some kind of serial still attached. So I was considering what options do I have. And after thinking a little bit, I noticed, well, I still have a Bluetooth module laying around, and everything is better with Bluetooth. So let's attach a Bluetooth module and go to serial over Bluetooth. Then I can close all of the case again, because there's lots of empty space inside. And that turned out to be a really good idea. Like the camera that I'm carrying around here, you can get through an airport with this one, even though it has been modified so that I get serial access. It's a quite useful hack. So if you have similar trouble, I really recommend doing it this way. So yes, let's have a look what we get on the serial interface. What I actually got is this. So there's a not too recent U-boot on it, and then it starts booting into Linux, kind of what I expected. They obviously just took the reference board design from some evaluation kit and modified it so that it's running. They didn't even bother to change the board string for it. And at some points it boots up into a login, so great. The first thing that I tried was, well, just put some obvious things like user or root or something. Nothing of that worked, but you can easily abort the boot process in U-boot and then get a U-boot shell and then, well, do whatever you want, like replace the init thing or whatever, change the root password, and that way get full access on the system. And then I could have a look like, okay, how are things actually connected? And I figured out, interesting, there's like the normal camera serial interface, and then there's a USB video class with the second camera. And there's only one binary running that has not even been stripped. So it has all the nice debug symbols, which can be useful for reverse engineering if it's required. I also noticed there's absolutely no optimization, like the kernel has ALSA enabled, networking enabled, Bluetooth enabled. All of this does not even exist in the hardware. So at that point, I was sure I can get it like a lot faster. So my plan was, let's switch to our own setup and get away from all this stuff that they did. So I had another look at U-boot and noticed, oh nice, they also kept like the default environment from the evaluation kit, which had like quite the complex boot command. And most of the functionality in this boot command is effectively unused. Like they are looking for boot script, but they don't have a boot script. They are looking for some firmware update thingy, but they don't have it. And there's also no option on the device to put something there. So that's completely unused. But what it meant for me is that I could like easily modify one of those commands. And I decided to replace the load boot script thing so that it's no longer looking for boot script on eMMC, but instead for boot script on the SD card. Which means I do not really have to modify the eMMC at all, apart from this really small modification. And now I can boot from an SD card by putting one in with a boot script. And if I don't do it, I still boot into the original system, which is quite great because if I fear that I broke something with my stuff, I can just reboot into the original one and make sure that it's still running as expected. So next, well, just prepare a boot script. Put some operating system on the SD card. Nothing too special in this place. I suppose most people here know how to prepare boot scripts and put some distribution on the SD card. I'm a Debian developer, so I use Debian, which does not really matter. Then I continued and just created a really small kernel. I started with the default IMX configuration that is mainline. Then first of all, I replaced all the modules to be built in, mostly because I just want to copy one image. It makes like the testing process for me a little bit easier. And then I went and disabled all bunch of things. Like the device has, well, technically mine has Bluetooth, but not exposed to the kernel. There's no Wi-Fi, so a lot of stuff could be disabled. I disabled modules because I don't use them. The CPU is single core, so I can disable multi-core support. Lots of things could be disabled, and that means that the kernel image gets smaller. I don't really care for disk space, but that loads faster, it uploads faster to the device, it boots faster, so the test cycles get a lot faster. For me, it was like going from 2 minutes per cycle to going to 15 seconds per cycle, so it's worth it. And then, just like I showed in my talk yesterday about the Rockchip, I used the same procedures to create a really small device tree, boot it on the device, and, well, try to get as far as possible, which turned out to be quite easy because basically all of the system on a chip is already supported. But quite early, I noticed an issue. The device has no hardware reset button. So if you do something and the device starts hanging, well, that's a problem because you need to open it up again and disconnect the battery, or wait some hours for the battery to run out, or alternatively make sure that it never hangs, which is not the greatest if you're just starting to work on preparing the kernel. Alternatively, the hardware needs to be modified. Have something in, like install a hardware switch yourself. So what I did instead was, first of all, enable the watchdog in the kernel. In that case, if it starts hanging, it will reset, will go back into U-boot. U-boot actually has a functionality that it won't boot the system if the power button is not pressed. So in this case, what actually happens is if the watchdog triggers, it won't reboot, it will actually power off, but then you can power it on again, and you don't need to really modify the hardware. So next I had to look for all the other components. So I rebooted into the original system and had to look at their sysfs, what kind of GPIs they're using. In their case, they just exported them all, like they didn't use any kernel support for it. The other part that I really recommend is they were new enough that we were already using device tree. Well, already, I mean, we've been using it for, I don't know, 15 years now. That thing can be decompiled, which makes it quite a bit easier to read it. You just need to be aware that the decompiling of device tree blobs, it won't bring you back all the references. So you just get numbers and need to follow them yourself. The other thing that I did was having a closer look to the messages printed by the bootloader. That was actually quite good because the setup that they're doing is they are just configuring the display from the bootloader and then never touch it again in Linux. And in the bootloader, one can see that they actually have an SPI-controlled display controller, and we want to have that properly supported in Linux, in mainline Linux, of course. The other bit is because the kernel does not really configure the SPI display controller, they don't have any information about the SPI port being used. So one definitely needs to have a look at UBoot for this kind of information, or go the try and error way, which might break hardware, so I don't recommend it. But before looking in the display, I first of all was interested in the USB-C port, because serial is nice, but it's a little bit slow, and the USB-C port by the original firmware is used to expose the device itself as a webcam, which means obviously it's, well, it can be used in gadget mode, and gadget mode can also be used to simulate a network device, and then I can SSH on the camera, which is a lot nicer than having to go over serial, especially over Bluetooth connected serial interface all the time. So I first of all got that running. All of the code for that is mainline, so that was not a huge issue. Nowadays, you're supposed to use config.fs to configure all of this. If people have problems with that, I prepared an extra slide at the end where I put my configuration. So next, I had to look at the hardware that was not working out of the box, which were actually not that much. The first thing was the battery stuff. As I mentioned at the beginning, I'm maintainer of that subsystem, so it wasn't that hard to figure out. The hardware has a small chip for charging the battery that basically works autonomously without any software interaction. It just needs a GPIO to tell, well, there's a charger connected, and to tell I'm done with charging, and that's it. We do have an upstream driver for that, but some modifications were required because it was not as generic as it should be. So that's fixed now. Everything for that landed in 6.5. The other bit is the display driver. As I mentioned, it has an SPI controller. It had an upstream driver, but it's really old. Hasn't been modified for like a couple of years. I started working on it and adding support. And for some reason, two other persons at the same time thought, hey, this is a nice controller. I also have a display using that. Let's update this driver. So we were like 3 people working on the same driver, which was a bit annoying. But all of those bits have also landed now. So the display should be usable as of 6.6. A little bit of special thing in this camera is the SPI controlled display. It's only have like a line going from the IMX to the display, but not the other way around. So you just send data and hope that everything works. If it doesn't, well, you won't see anything, but you cannot fix it. So last but not least, the most interesting part, the cameras. After a closer look, the camera serial interface, that one is used with an optical sensor. So the thermal cameras usually overlay a thermal image with the normal optical image to produce a more easy to read image. If we go back to my initial picture, this one is actually an overlaid image, only slightly, but on the left you can see the connector, and that wouldn't be that easily visible if you just have a thermal image without any optical data inserted into it. So this sensor is connected to the camera serial interface. And unfortunately, this sensor does not yet have any mainline driver. There's a public data sheet where it's, well, at least for me, it's really hard to read because it only has the sensor names and a vague description of what they're supposed to do. It's full of abbreviations and they are non-obvious. And it's quite complex because it has image signal processor capabilities, which the camera kind of needs because the IMX6 ULL does not have any image signal processor. I found a bunch of out-of-tree drivers. None of them are working at all. Like if I use them, there's absolutely no image. So I tried using one of them and use them as a base and then start hacking on it. I did find a register which enables test modes, and after a few weeks I got this. So I was quite happy. But after disabling test mode, it looks like this. And that's actually an image from yesterday that I did in my hotel room from the remote control for the TV. Might be quite hard to see. So this is actually the current state that I'm at. So I'm still working on that one. I do have some problems with the image signal processor part, and as I said, it's not that well documented. So yeah, that part is work in progress. The other camera that's inside, I guess the most interesting one, we are talking about the thermal camera, is the thermal sensor. And that one is connected over USB. But it kind of lies about the data format. And also, in addition to the UVC interface, it needs some vendor commands for like all kind of instructions. We need to configure if we want to be in a high gain or a low gain mode. So the camera differs between that. High gain means I want to see temperatures between 0 and 100. And if you are interested in temperatures way above that, you need to go into low gain mode. So yeah, there are controls like that, then calibration data. And that's like quite vendor specific. So I mentioned it lies about the data format. You can see that I have like a GStreamer pipeline that like modifies data a little bit. If it's not modified, you actually get this kind of picture. So that's not really what I expected. After applying the pipeline, I got to this. So on my one hand, there's some ice, and on the other hand, there's a lighter, with the idea to have like the minimum temperature and the maximum temperature to figure out how to, well, interpret the data. I'm actually still working on that part. As you can see, I get, well, some kind of image, but I do not yet have like the absolute temperatures, and in some cases I still see some glitches, so it's not yet perfectly reverse engineered. But if you remember, there was another serial interface, and I was like, okay, let's have a look on that one. It has a really weird baud rate, but then once you connect an adapter and read it out, you see, oh, there's another U-boot. And it's a bit more recent. And it's a completely different platform. So apparently the sensor itself is also running Linux on some kind of MIPS machine from Realtek, which is usually used for IP cameras. And that one is, well, a lot more optimized. If you've seen the board, it's also like a lot smaller. And so I had a look at the board itself. It's labeled InfiniRay, which apparently produces thermal imager sensors similar to FLIR, but based in China. And unfortunately, that system on a chip, it's completely unsupported. There's absolutely no hint in the mainline tree about this system on a chip at all. And when I was doing like some probing with the oscilloscope on the module, I accidentally broke one, which means I had to get another of those cameras for the talk. So for the moment, I'm focusing on the IMX6 side and not on this extra chip. I plan to come back eventually once the IMX6 side is done. So right now I do have some open issues. I could find a few of those vendor commands, but others are still open. So I did find a project that was reverse engineering a different camera from InfiniRay. So I thought, well, it's from InfiniRay, they probably will use the same sensor. Let's have a look. I actually found a picture that also looked like this greenish, so I thought, oh, great, that's probably that. And there's already a project that started reverse engineering this specific camera. But unfortunately, the protocol that they're using for the vendor commands is completely different, like it's using completely different opcodes. So that's not really usable, which means the reverse engineering needs to be done, well, by somebody else, probably me. And as I mentioned, like the binary is, well, completely unstripped. So all the debug symbols are in there. I started looking at it with Ghidra at the moment. The other part that I did was like just put an S-trace binary in the original system and have a look at what it is sending over USB. What's unfortunately not possible, and it would make things a lot easier, is running this binary from the mainline kernel, because the interfaces are quite a bit different because of all this GPIs and all of it. It's quite hard to run it. So I'm considering maybe writing some kind of wrapper for it, but that already would quite a bit of work, and the Ghidra thing is actually working quite well. So the thing that, well, I'm currently thinking about is how will we handle it actually upstream once I figure out the interface, because, well, these custom things, we don't have anything right now in Video for Linux for it, and it needs all kind of interesting things like calibration data and these gain modes. So I'm still wondering how to expose this, and if we even want to expose this or just handle everything in user space. If somebody has ideas about this, please contact me. And with that, that's it from my side. If you have questions, please ask.
Hi. Thanks for that work, but one of your initial slides showed that you are that the original product was using 3.18 something kernel, right?
Yes, it's a quite old kernel.
Yes, that's for Greg. Okay, and the next one, one of the other slides that was showing 4.9.51. Is that the kernel that you are using, or are you using mainline?
So the kernel that I'm currently running now,
yep,
is 6.6 release candidate 3 from last Sunday.
So if you please go back to the some slides back, one of the demessage was showing 4.9.5 by 1, I think. Where you are saying about the second U-boot, yeah, the second serial port. Yep, this one.
This one.
So is this a second kernel running on that board, or because this is 4.9.51, the first slide was showing yes, 3.18.
So this is the system running on the sensor.
Right. Okay.
That's untouched. Like at the moment, I didn't do any work on this sensor itself.
Right. Great. Thanks.
You're welcome.
Do you know any sort of like collection of BSPs with Linux, like for GPL compliance, like maybe like somebody like a organization just hosts all of the BSP Linuxes that like for example for this architecture?
I haven't looked if somebody already complained about any GPL violences for this platform. I haven't even looked that much if somebody already got the source code. As I said, like I broke one of the sensors with the oscilloscope, so I didn't try too much to change the firmware on that one.
Gotcha. I was just wondering if there was like a project that basically took all of, because there's so many out of tree stuff that just took all of these like miscellaneous architectures and just shoved them into one repo or one like group of repos or something like that. If you knew anything like that, or if anybody knows anything like that, that would be pretty useful too.
it would be useful. I don't know any project that does this. Maybe somebody else does.
Any other questions?
Just to mention that in the context of thermal cameras, we recently had people looking into supporting them using directly USB commands instead of showing them up as UVC devices. If I got you correctly, this chip here registers as a UVC camera
Yes,
input.
it does.
So you are supposed to interact with that with the Linux API, basically. Recently, there is people which is looking into supporting this kind of devices as raw USB devices without going through UVC. If you're interested, I can put you in touch to see if there is anything related to this one. I'm not sure if that's connected or not, but
Yes,
we can discuss it.
please do. Thanks.
Okay.
There was one other.
For debugging or reverse engineering the user space application, you mentioned that it's not possible to do that with the 6.6 kernel, but could you just build a rootfs for the 3.14 kernel, where in that rootfs you have GDB, strace, whatever tools you need to reverse engineer it, and then run the application under that rootfs?
Yes, so it is possible, of course, to build applications for the other system. The rootfs of that has, well, it's a little bit limited. So I did mention that I was running strace before. That was like a static compiled strace that works in the original rootfs. So it is possible. It's just a little bit annoying to, well, build binaries for it.
Always watch for the microphone. There was one other question I thought I heard. No? Are we good? Okay, thank you, Sebastian.